to help you better understand rational expression operations, and that includes multiplication, division, addition, and subtraction, but also kind of general simplification of rational expressions and an overall attentiveness to values that cause this rational expression to be undefined. And generally, we're looking to the denominator to determine where that's happening. So let's work through a few of these problems and see if we can highlight some important qualities. For instance, in number 1 here, this is actually as much of an exponent operations problem as it is just simplifying a rational expression, although we do have this kind of classic some value, some number being compared to some other number. If you want to be a little bit more technical, you're comparing a polynomial to another polynomial, and that's what defines a rational expression. So as I adjust my marker here, you'll notice that in the numerator, I've taken everything inside these parentheses and raised it to the third power, which is how I ended up with negative 125, m to the third, n to the sixth. Nothing is happening to this denominator. And I'm very kind of meticulous about including my equal signs to show the progression of the problem as it becomes more and more simplified. At this stage, I recognize that negative 125 is divisible by 5, leading me to negative 25. And these sorts of exponent operations I can kind of do mentally. I recognize I have more of these m's in the numerator than in the denominator. So just one m left in the numerator. N to the sixth over n to the fourth ends up being n squared. And so there's our first answer. Problem number 2 is really difficult to approach as far as simplification is concerned until you factor everything completely. And this is kind of a recurring theme for us this year, that it's oftentimes difficult to make any progress if the form of whatever you're looking at, whatever mathematical expression you're looking at, is not factored. That's not to say that factoring is always the right move, but it frequently is. So I'm actually factoring in steps here. Step 1, I recognize that in the numerator, both terms had a 6 in common. In the denominator, all terms had a 14 in common. But it doesn't end there. This binomial is what we call difference of squares, and its factored form is x plus 1 and x minus 1. This trinomial can further be factored into an x minus 1 times x minus 1. And at this stage, I'm able to take advantage of the fact that certain factors are showing up both in the numerator and denominator, like this x minus 1 shows up in both. 6 and 14 are both divisible by 2, which leads me to have 3/7. And this is the final answer. Now, I do want to pause for a minute and say that there is a danger. I have not been asking for excluded values here, but oftentimes the temptation is to look at the simplified answer and to simply say, well, x cannot be equal to 1, because if it is, you'd end up with a 0 here, and 0 times 7 is 0, and division by 0 is undefined in math. But the truth of the matter is you kind of want to go here before any terms have been crossed out. Now, it so happens that the other factor was also x minus 1, so it doesn't make a difference. But let's say this was x plus 1, for instance, and there was no x plus 1 in the numerator, then you would have to also include a negative 1 here as an excluded value. So what I'm suggesting is, look at your unsimplified version of your answer. That's where you will find your excluded values, generally, almost always, in the denominator. Moving on to question 3, it appears as though things are different, but they're really not. We have a multiplication problem. I like to cross-simplify, not cross-multiply. In other words, I like to look across and see, for instance, this 6 and this 8 are both divisible by 2. And I would, it's my personal habit to begin simplifying here. But for the sake of kind of making this easier to understand visually, I've written the entire numerator out and the entire denominator, being really careful to arrange the variables in alphabetical order. And even though I've not done any crossing out here, initially you can see, for instance, that I decided that 25 and 20 were both divisible by 5, which gave me a 5 and a 4. Right? Same 5 and 4 you see here. 6 and 8 were both divisible by 2, which gave me a 4 over a 3. So I just want you to kind of be aware that these values are not magically appearing. I've got a squared over a to the third. That means there's more a's in the denominator. And I just kind of simplify sequentially, step by step. I'm able to keep track of both my numerical values and my variables. Final answer, 5by over 3ax. And if I was to kind of report excluded values here, this is where I would go. I'd want to say that a, b, x, and y, none of them can be equal to 0, because if they were, we'd have an undefined expression here. And these undefined values are going to become more and more relevant as we study these rational functions. Some things to notice about problem 4 are that it initially starts out as a division problem. You may well know at this point that division of fractions really means multiplication by the reciprocal. So I intend to leave this first fraction intact. Just grab a different color here. I'm going to leave this first fraction just as is, but I'll be multiplying not only by the reciprocal of this fraction, but also I'm going to first take all these values and square them. So that's how I got this 16x squared y squared, and this z to the third became z to the sixth. And then I kind of flipped it in order to find its reciprocal. And now I'm multiplying, same as I did up top, writing all the values out. Here's my final answer. Number 5 actually ends up being quite analogous to number 4, because this giant division sign can be thought of as this kind of classic division sign. And it just means to me, leave this entire numerator as is, and then multiply by the reciprocal of this fraction down here. So that's what I've done. But in addition to doing that, I decided to factor everything as I went along. You'll notice that all of these three terms had a 5 in common. And then I factored the remaining trinomial. So what you see here, this 5 times x minus 3x plus 2, is the factored form of that numerator. Same with the denominator. They had a 15 in common. I factored that out, 15 times 3 minus x. And I'm multiplying by the reciprocal, so you'll notice that this 4x minus 12 becomes 4 times x minus 3, also factoring the denominator. And at this stage, I kind of ran out of patience for wanting to write the entire numerator and the entire denominator out over and over again. So I am beginning that process of, okay, I've got an x plus 2 here. I've also got an x plus 2 here. They will eventually be, arranged as one big fraction where x plus 2 over x plus 2 is another name for 1. These x minus 3's cancel out. 15 and 5 divisible by 5. So you kind of get where this is going. This is a step that bears a little bit of explanation. At this point, it does look like you're at a dead end, but you're actually not. This is not a dead end. The binomial x minus 3 and 3 minus x look really, really similar. They are not the same thing. But in order to create the same binomial, I factored a negative 1 out of this binomial, removed a negative 1, and that's why this positive 4 becomes a negative 4. And the signs here change. This negative 3 becomes a positive 3. This positive x becomes a negative x. And in doing that, I have not changed what this means, simply how it looks. And it allows me to cancel out these 3 minus x's, cancel out these negative signs, and simply end up with 4/3. This is kind of the challenge of simplifying, the ability to see these insights so that you can simplify further. Here in problem 6, we were given this equation and asked, was it sometimes true, was it never true, or was it always true? And that's why I'm putting a question mark here. And a lot of you said, well, let's just replace d with different numerical values, and that's kind of a nice way to explore. The problem is you can't exhaustively plug in every potential value for d. So one way to check to see if this is true sometimes or never or always is to cross multiply. If a proportion is true, then its cross products should always be equal to each other. So here you see me finding cross products and asking, is this true? And at this stage, this juncture here at the very end, I ended up with the equation 60 plus 15, wondering, is that equal to 60 plus 10? And the answer is no. The 60's cancel out, and 15 is not equal to 10. And another way to think of that is, no matter what you plug in for d, it'll be 6 times as much on this side, 6 times as much on this side. But the left side is always having something different added to it. It's having a 15 added to it, whereas the right side is having a 10 added to it. So it is impossible for those two sides to ever be equal, and that's one way to show it algebraically. Here are the remaining problems with the exception of 11. In problem 7, we were asked for what values is the expression undefined, and so you'll notice that again I'm kind of hyper-focusing on the denominator, which, lucky for me, is already factored, partially at least. So when is d plus 1 equal to 0? Well, when d is equal to negative 1. Here, I decided to factor further, d plus 2, d minus 2. And when d is negative 2 or positive 2, again, we're going to equal 0, and we don't want that. So I wrote two versions of the answer. One is the expression is undefined when d is equal to negative 2, negative 1, and 2. Or this can be reported as d cannot be equal to negative 2, negative 1, or 2. These are different versions of the same answer, and I'm being very careful about the way that I report those answers. Let's take a look at some addition and subtraction. That's a place where students oftentimes need the most help. And I'm not quite sure. Let's see if I can zoom in a bit here. I think I perhaps can. There it is. And you'll notice that initially I can't subtract these fractions because they have different denominators. And so what we do is try to give them a least common denominator, oftentimes expressed as LCD, also similar to LCM. Least common multiple and denominator oftentimes mean the same thing. If the multiple is actually in the denominator, well, now it's a least common denominator. So 4 and 6, 12 is divisible by both 4 and 6, and it's the smallest such number that has that quality. And then I've got my xy squared. So here is my least common denominator, and I arranged this problem vertically. I thought perhaps it would be easier to see what's going on. I want to assign both of these fractions the same denominator of 12xy squared. In order to do that, I have to change this fraction to turn it into an equivalent fraction. So I'm asking a question. And the question is, what am I multiplying 4y squared by in order to get 12xy squared? And the answer to that question is a 3x. What you do to the denominator, you do to the numerator as well. And so this existing 3x times this new 3x produces 9x squared. Same thought process here in the denominator of this other fraction. Somehow this 6x became 12xy squared. How? We multiplied by 2 to get to 12, and then y squared. Same thing has to happen here in the numerator. Let's multiply by 2y squared, and in doing so, we get 2y cubed. Now that they have the same denominator, that frees us up, kind of gives us the green light to simply write 9x squared minus 2y cubed all over the least common denominator. And now there's no further room for simplification. In the upcoming problem, I think I took a slightly different tact, and that was, let's see, I also wanted to find a common denominator, but I wrote this out using a horizontal arrangement. So here are the original denominators. You'll notice that if I draw some connecting lines here to make it a little bit easier to follow visually, I factored out here, and I factored out here so that I could more easily identify that the least common denominator was 3 times m plus 2m minus 2. Again, one way to think of it is this value, this expression, is divisible both by m plus 2m minus 2. You can see them literally inside of my answer. And it's also divisible by 3 times m plus 2. Same game is being played up top. I start out with an m. What am I multiplying m by? Well, the number 3, because I multiplied the denominator by a 3. Same thing has to happen here. What did I multiply this by? Well, I multiplied it by an m minus 2. So you'll notice that the existing numerator of 2 gets multiplied by m minus 2. From this point forward, all I'm doing is simplifying. I'm distributing the 3, distributing the 2, adding like terms. I do want to say something about this last step. I was dissatisfied with leaving the answer in this form because the numerator is expanded, but the denominator is still factored. And so I thought that for the sake of uniformity, to be consistent, let me distribute the 3 so that both numerator and denominator are in expanded form. So you don't have a mismatch of expanded and factored all in one. So from there we go to problem 10 as I scroll down a bit. And this is the last problem we'll go through. It looks really kind of complicated at first glance, but in fact it's not so complicated. Once more, you'll notice that I start out by taking the respective denominators and factoring them. Here's the factored form of the first and the factored form of the second. That makes it much easier for me to identify the least common denominator, and here is that least common denominator. This denominator is divisible by both of these previous ones. You might be able to tell that I've got some black ink versus blue ink. The black represents the original numerators of d minus 4 and d plus 2, and the blue represents what I'm multiplying by. Here what I did was separated the numerator and denominator because each of them required quite a bit of work to expand and simplify. So here's my math work for the numerator, where I'm multiplying these binomials and then carefully bringing together like terms till I end up with negative 8d plus 20 as my numerator. Excuse me. In my denominator, I'm multiplying out d plus 4 and d minus 4, which gave me d squared minus 16, times the remaining d minus 2. And here is that new denominator. And finally, I just arranged them here so that you have my final answer again, both written in expanded form. I do hope it's been helpful to see not only the solutions here, but kind of the step-by-step process that I went through in order to work through these rational expressions. Thanks for watching.